converges, and the sum will be equal to a by 1 minus r. And if absolute of r is greater or equal to 1, then this series diverges. Let's see an example. This example consists of three parts. In the first part, r is equal to 1 by 3. This is the geometric series with first term a is equal to 1 and a is not equal to 0 and r is less than 1. Thus, this summation will be equal to a over 1 minus r, which is 3 by 2. Similarly, in second part, we can write this sum in this form, and which is equal to a by 1 minus r, where a is equal to 1 and r is 1 by 6. So the sum is this. In part C, this is the sum, and which can be written in this way, and according to the formula a over 1 minus r, here r is 1 by 5, we may also think of this as the series I is equal to 0 to infinity. If 0, I varies from 0 to infinity. With the first term removed, the sum is then 1 over 1 minus r minus 1, which is again 1 by 4. These are some rules for series. Sum rule. If we have summation ai and summation bi, and we both converge, then sum will also converge and can be written as in this form ai plus bi, summation of ai plus bi is equal to summation of ai plus summation of bi, and the constant multiple rule. If summation ai converges and c is any real number, then sum of cai also converges and can be written in this way. These are the algebraic rules for series, which will be used later on. Sum the series, and series is given here. We can write in this form, and simplifying 3i by 6i, we can write it 1 by 2i. Similarly, 2 by 6i can be written as 1 by 3 whole power I. If we take minus 1 as common, just writing this negative sign, replacing this negative sign with positive, we have to write here minus 1. These are the sum of two series, this series and this series, or convergent, with sum 2 and 3 by 2. The algebraic rule implies that this can be written as in this form, which can be written here with separate summation notation. We will write here 2, this minus 1, and this sum 3 by 2. Finally, we obtain 1 by 2. The ith term test. If we have this series which converges, then the limit ai, where I approaches to infinity, is equal to 0. And if this limiting value is not equal to 0, then the series summation ai diverges. And if limiting value is equal to 0, then the test is inconclusive. The series would converge or diverge, and further analysis is necessary. This is called the ith term test. If the summation converges, then limiting value of ai will be equal to 0, and if limiting value is not equal to 0, then the summation ai will diverge, and if limiting value is equal to 0, the test is inconclusive. The series may converge or diverge. Let us discuss an example in the light of the ith convergence test which we are discussing. This example consists on 3 parts. We have to check the convergence of the series in the light of ith term test. We know that ith term test indicates about the convergence of the series if we are already aware of that series converges, then limiting value will be equal to 0. And if we want to find the result about the convergence or the divergence, we will check the limit of the ai term. If it is not equal to 0, then series will diverge. And if the limit approaches to 0, then the test is inconclusive. First, we discuss about the A part, and we want to find out the limit as I approaches to 0 of this AI. We can easily calculate this limit, and we will conclude that this limit does not approach to 0. And if this limiting value does not approach to 0, then according to the Ith term test, or a part, the series will diverge. This will diverge. This is divergent test. Now, if we want to find the result about the B part, again, this is AI, and we calculate the limit as I approach to 0. I approach to infinity. This is the absolute, and this part can be again tested. This will also diverge because the limiting value will not approach to the 0. And for the third part, an or ai, ith term with 1 over I. And if we test its limits when I approach to 0, the limiting value will approach to 0 as I approach to infinity. The ith term test says that if the limiting value approaches to 0, then the test is inconclusive. We cannot conclude about its convergence or the divergence. This is the solution, as we have discussed, that this approach to 1, not to 0, as I approach to infinity. Because if we divide here or take common I from denominator and numerator, we will get this form, and applying limit as I approach to infinity, this whole term approach to 1. Since our AI does not tend to 0, if it does not tend to 0, then according to the ith test, series must diverge. So a part has the solution that the series mentioned in a part diverge. Now for the B part, take absolute value of AI, which will be I over square root of 1 plus I, and writing it in this form, taking common or dividing numerator and denominator by the I square root, we get this form. Now we have to apply the limit. This approach to infinity, denominator will approach to 1, while numerator consists on the square root of I. This approach to infinity as I approach to infinity. Thus AI does not tend to 0 here. Again, this series also diverges in B part. In C part, we could not conclude about the convergence or divergence of the series because AI is 1 over I. And if I approach to infinity, this approach to 0, so our test is inconclusive.